In this video, we're going to bring together a lot of things we talked about so far and talk about just analyzing arguments in general. So first of all, we're going to talk about what a tautology is and identify a tautology. Then we're going to use a truth table to analyze an argument. So note that we've already analyzed arguments already in this course. We've done so using a logical syllogism and Venn diagrams and often together. And note that in order for an argument to be valid, the conclusion needs to be guaranteed, and that is under any circumstances. So we saw an example in our first video that said that we had this logical syllogism that some plants are poisonous, broccoli is a plant, therefore broccoli is poisonous. Now we know that argument to be invalid, but we need to understand why is it invalid. And we talked about this again, but this is a review of this sort of idea. We can look at these Venn diagrams here and look at two different circles representing plants and poison together. And there are two options for where X goes. There are two options for X. X being broccoli. So you could put X in the first option just in the plants but not poison circle, or you could put it in the intersection between them. And if you put it in the intersection, well then yes, broccoli is poisonous. This would be like a true statement. But if you put it outside, then it is false. And broccoli is not poisonous. So therefore, this argument is not valid because there is a possibility that we get a false statement. When we want to look at the validity of an argument, if we want to say an argument is valid, then we want to say that every possibility will give us true. Now we've looked at a bunch of truth tables in the last few sections, and we get a bunch of true-false statements for different arguments. We're going to try to focus on it being true in that last column, and that's going to tell us something about the validity of the argument. So before we start talking about truth tables, let's talk about the general form of arguments that we're going to have. The previous one that we had is a very specific form, this logical syllogism, where there's two premises, a major premise and a minor premise. They're always in the exact same form, and we can say some stuff about that we already have. In general, we can have as many premises as we want, right? So here's an example where we have n premises, P1 to Pn, and then we have a conclusion from that. So what this is saying, if we have a bunch of premises and a conclusion, we want to say that we have the first premise and the second premise and the third premise and the fourth, all the way to the nth premise. Remember that these symbols in between represent the word and. So if we have all of those are true, this and that and that and that, that has to imply the conclusion C. And that's what any argument is going to kind of be about, is we have a bunch of different premises, and together they imply some conclusion. So what we're going to look at here is to find an argument is valid, we want to show that it is a tautology. So a tautology is a statement that is always true. So in mathematics, we have a bunch of tautologies. These are these formulas that we know to be true. Right? We have like we have a squared plus b squared equals c squared, the Pythagorean theorem. Right? That's a tautology. If we think about a right triangle, we have, a plus b squared equals a squared plus 2ab plus b squared. That is a tautology because both of those things are equal under any circumstance of a and b. So to find an argument is valid, we want to show that this statement, P1 and P2 and P3 all the way to Pn, implies C. That is valid if and only if it is a tautology. And we talked in the last video that if and only if we think about as a biconditional, write it as the double arrow, if and only if we think about it as an equal sign. Right? The argument is valid is the same thing as saying it is a tautology. All right, so bringing into the idea of a truth table now, let's look at this example. So we're going to use this truth table to analyze the validity of the following argument. So note that in this argument, we're going to have two different simple statements, P, which is going to be he is illiterate, and Q, he can fill out an application. So the first premise is, if he is illiterate, he can fill out an application. And we can write that symbolically as an if-then statement. P implies not Q, right? He cannot fill out an application, so that is not Q. Our second premise will be he can fill out the application, so that is Q itself. And our conclusion is, therefore, he is not illiterate. So we have this symbol we haven't really talked about yet, this 3 dots here. That's going to be therefore. We'll use that a few more times today. Therefore, not P. He is not illiterate. So we have two premises and a conclusion. And now let's talk about the validity of the argument. So we're going to use this truth table to basically find our argument, which is if we take our two premises 1 and 2, here we have 1 being our first row, second our 2 our second row. Here's 1, here's 2. If we take 1 and 2, that has to imply C. So we have 1 and 2 implies C. So in our truth table, we're going to have our P and Q because we have two simple statements. We're going to have 4 rows to our column. We need to find not Q in order to build our premises. Our first premise is that first row in the column. Right? This is our first row. P implies not Q. Our second premise is our second row, Q itself. Then we want to kind of put those together. We're going to do it step by step. So we have 1 and 2. That's P implies not Q and Q. Then we have our conclusion. That's going to be not P. And then we're going to bring it all together with this big argument. So again, this is our argument that we want to see. But as we've done so far with truth tables, we want to build up that argument piece by piece so that we can kind of simply do it each step of the way. So let's look at this truth table. Remember, we start out with a true, true, false, false for P, true, false for Q. That's every possibility of P and Q together being true and false. So not Q is going to be false, true, false, true. It's the opposite of Q. To do P implies not Q, you want to show that P has to be true and not Q has to be true in order to be true. If P is true and not Q is false, that gives us a false. And if P is false, we have a vacuous truth, T. So therefore, the only time we have false in that implication is when we have the antecedent be true and the consequent be false. All right, we've already done Q. I just wanted to write it again so we can know that's going to be the second row. So we'll just rewrite Q here. That's true, false, true, false. So then if I want to do 1 and 2, the first premise and the second premise, the first row and the second row, I need both of those to be true in order to get the and to be true. So that means that we are going to have a false, 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 true. Only the third row here is going to have both of those be true. Note that our conclusion is not P, so we can kind of put that in there. Not P is false, false, true, true. And now we can talk about our argument. This is our antecedent. This is our consequent in our big conditional. So we want to say if the first thing, if the antecedent, then the consequent. If P implies not Q and Q implies not P. So note that we have vacuous truth in the first, second, and fourth rows because the antecedent is false. And we have a true in the third row because we have both of them being true. So this is what we call a tautology. Under every possible circumstance of P and Q being true and false, that is any possible thing that we always get that this argument is true. So therefore, the argument is valid. It's like we could look at these Venn diagrams. These would be very complicated Venn diagrams, and if you could put X in any possible place in the Venn diagram that makes sense with the argument, you would always get that that would be true given the argument. But we're doing it with a truth table, which is much quicker than that. So we're looking for all truths, and the last row is a tautology. A tautology is the same thing as saying the argument is valid. All right, let's try it again. This time, we're not going to have the a worded argument, but just talk about a tautology in general. So here we're going to have P and Q implies P or Q. We want to show that that's a tautology. That is that the last column is going to be all truths. So we start with our truth table. We have P and Q means that they both have to be true in order to get a true. That is only going to be the first column. Next, we have P or Q. That means that we only have to have one true in there. That's going to be true, 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 false. And then we want to show that P and Q implies P or Q. Note that we have vacuous truth in the second, third, and fourth columns. And we have a true in the first column because they're both true. So therefore, this is a tautology. So this is a tautology. We don't really have an argument here, but we just showing that a tautology is some kind of statement that's always true. It doesn't necessarily have to be in an argument. All right, next example. Going back to our worded arguments, use a truth table to analyze the following argument. If the defendant is innocent, the defendant does not go to jail. The defendant does not go to jail, therefore, the defendant is innocent. So I urge you to pause the video for a second and try to think of the following things. First of all, what are the simple statements that are being used in this problem? There are two. We're going to call them P and Q. What are the premises that we're talking about here? These are like the hypotheses that we're giving in our argument, the initial conditions that we're giving. What is the conclusion that we're making? And how can we write those symbolically using P and Q? If you have that, then take a second and just try to determine, do you believe that this argument is valid? If someone told you this in an everyday life and you had to make the determination whether it's valid or not without doing a truth table, would you say it's valid? Why or why not? Take a second and do that on your own. Come up with an answer, and then we'll determine whether it's true together. All right. So there are two statements here, P, Q. The first statement is the defendant is innocent. The second statement is the defendant does not, or the defendant will say goes to jail. There's more than one possibility that you could do here. You could say the defendant does not go to jail, but usually we have our simple statements be positive things. We don't have too many negatives in there. So we'll say the defendant goes to jail, and then we will use a not in our argument. So our premises, we have two different premises. Our first one is this first sentence. If the defendant is innocent, the defendant does not go to jail. If the defendant is innocent, the defendant does not go to jail. And we can write that as if P, then not Q. And note that that is going to be our first premise here. If P, then not Q. Our second premise is the defendant does not go to jail. So we can write that as not Q. The defendant does not go to jail. So that's going to be our second premise here. And our conclusion is, therefore, the defendant is innocent. That is just P. We'll say, therefore, P. So that is our conclusion. Therefore, the defendant is innocent. So note that our argument, we want to have the first premise, P implies not Q, and our second premise, not Q. And then our argument total we'll write as P implies not Q and not Q implies P. So that's what we're trying to show in this argument, whether it's true or not. So note that we should probably figure out not Q in order to do this. So not Q is false, true, false, true. So P implies not Q. We have vacuous truth in the third and fourth columns because P is false. We have that the first column or the first row is going to be false because we have true in the antecedent, false in the consequent. Remember, we're using our first two rows there, first two columns. And the last one will be, or the second one will be true because we have true both the consequent and the antecedent. All right, so our first premise, false, true, true, true. All right, 2 is going to be not Q. We've kind of already found that. That's going to be false, true, false, true. So putting those together there, we're only going to get true if both parts are true. Note that that's going to give us a true in the second and fourth row and false in the first and third. Our conclusion is P, so we're just going to write that again. That's true, true, false, false. And then we think about our big argument, if 1 and 2 implies C. So note that we have vacuous truth in our first and third row. We have a truth in our second row because we have true in the antecedent, true in the consequent, but we have false in the fourth row because of the false in the consequent. So therefore, this argument is not valid. And that's all fine and good. We know mathematically this is not valid, but let's talk about why it is just in the English language and without going through all those details. We said if the defendant is innocent, the defendant does not go to jail. We said the defendant does not go to jail, therefore the defendant is innocent. And really what this is saying is we have a conditional statement, if the defendant is innocent, the defendant does not go to jail. And then we talk about the converse of that statement. So note that this whole thing is the converse of our statement. And the converse of a statement is not always true. And that's what we're kind of seeing in this argument. If somebody was giving this argument, they're saying that because it's true in one direction, it has to be true in the other direction as well. Then we know that's not possible all the time. So in this case, this argument is not valid, and we can see it with a truth table. All right, let's do one more example. This is kind of a weird one. We're going to look at more simple statements, more premises, and talk about how to kind of build this argument. So this kind of odd argument we have, no ducks waltz, no officers ever decline to waltz, all my poultry are ducks, therefore my poultry are not officers. So let's first talk about the premises here. We have three of them. First, no ducks waltz. That's our first premise. Second premise, no officers ever decline to waltz. Third premise, all my poultry are ducks. And conclusion, therefore my poultry are not officers. So it's saying like if no ducks waltz, and if no officers ever decline to waltz, and if all my poultry are ducks, then my poultry are not officers. That's the argument that we're trying to make. So to put this symbolically, we need to have some work. Note that even though we only have three premises, there are four simple statements in here. And it just takes that first premise to look at that you cannot write that as a simple premise itself. Or you could, but breaking it up will help us look at the differences between the first and the second and the third premise, as we're going to have to need just ducks and just waltzing in different premises. So our simple statements are going to be, it is a duck, it will waltz, it is an officer, and it is my poultry. And we're going to translate our premises into some if-then statements. So instead of saying no ducks waltz, we could write this as, if it is a duck, then it does not waltz. That's putting it in terms of our simple statements, breaking it up into something with ducks and waltzing separately. And this will be P implies not Q. Our first premise, we'll call that 1. The second one says, no officers ever decline to waltz. That means if it's an officer, then it does not decline to waltz. We could write that as R, it is an officer, implies not Q. And that's a little bit awkward, and saying does not decline is an odd thing to say in the English language. So equivalently, we could say if it is an officer, then it will waltz, which is just R implies Q. And we'll call that our second premise. Our third premise, all my poultry are ducks. We could write that as, if it is my poultry, then it is a duck. and that is going to be S implies P, our third premise. Finally, therefore, my poultry are not officers. We could write that as therefore, if it is my poultry, then it is not an officer. And that is the same thing as saying S implies not our conclusion. So this takes some getting used to, this kind of idea of breaking up this argument into different simple statements. These simple statements are the bare bones of our argument, and we're piecing them together in different ways. And there's not just one right way of doing it. So for instance, we could have done R implies not Q, and we could get the same answer. It just is going to require more work, and it might be a little more awkward. And there's other things that we could have done as well, but would be not as straightforward as the one we did. Okay, so now we're going to do a huge truth table. Before we look at it on the next page, let's talk about what we should expect to see. We have 4 simple statements. So therefore, we should expect to see 2 to the 4th 16 rows in our truth table. That is all the possibilities of P, Q, R, and S being true and false together. Then we're going to try to build our 3 premises, 1, 2, and 3. And we are going to build our conclusion, and then we're going to bring it all together, 1 and 2 and 3, and then 1 and 2 and 3 implies Q, or implies C. So let's look at this truth table. 16 rows, as promised. We have our 4 simple statements, P, Q, R, and S. Let's talk about how those are built for a second. You do half true, half false for P. Then you do half of those are true, half of the trues are true, half of the trues are false, and then repeat. So it's like we're doing 4 trues and 4 falses. Then we do 2 of those are true, 2 of those are falses, 2 of those are true, 2 of those are falses, on and on and on and on. And then at the last step, we alternate true, false, true, false, true, false, true, false. And I won't do that all the way down. Okay. In order to build our premises and our conclusion, we need not Q and not R. So we build those 2 columns as well. Then we do our 3 conditionals, our 3 premises, put them together as 1 and 2 and 3. So let's look at that little thing right here. Let's pick out a couple of these. So we have 1 and 2 and 3. 1 and 2 and 3, since 2 is false in this case, they all have to be true to give us a true, so the conclusion is false, the 1 and 2 and 3. Whereas in this row, we have them all true, so therefore the 1 and 2 and 3 is true. And let's look at the conclusion, or not the conclusion, but the entire argument here. 1 and 2 and 3 implies the conclusion. And let's do another one. How about this one down here? We'll just kind of pick some random ones to kind of show where they're coming from. Here, this is a vacuous truth because the antecedent is false. And then here we just have a true statement because we have true than true. And note that no matter how we build it, this is always true. In all 16 cases, we get this is true. So this argument is valid. So next, we're going to continue thinking about the validity of arguments And we're going to talk about some general forms of specific arguments that we know to be true.